Good morning. And the last topic we are going to look at this week is the Bose gas. We have already derived the distribution function or density distribution for the Bose gas. And today we are going to look at two particular applications. First, we are going to look at the case of photons. Photons are the quanta of the electromagnetic field. Okay? They are bosons, and their number is not conserved. Okay. For example, when a photon gamma is absorbed or created by an electron, then we have an equilibrium condition for such a reaction, as that original chemical potential was mu of the electron, and at the end it becomes the chemical potential of the electron plus the chemical potential of the photon. It immediately follows that chemical potential of photons equal to 0. So, because their number is not conserved, they can be created out of nothing and they can be absorbed. Okay, with just the energy increase or decrease. A photon normally it has two polarization states. It's either left and right circular, or when wave vector is moving just in circular directions, clockwise or anti-clockwise, or vertical or horizontal. And it travels at the speed of light c. A dispersion relation, which is the energy as a function of its momentum for a photon, is simply given by this expression, and we already seen this in one of the tutorials. Okay, and so it's proportional. It's a linear function of p, not quadratic. And if we define the wave number and the frequency omega by standard formulas like this, then we can relate the momentum to the frequency. Okay. Then the energy obviously becomes, if you substitute here for the formula for the momentum, it obviously becomes h bar omega. Okay. Now, black body radiation. Maybe some of you already heard about black body radiation, but let me explain a meaning of that. So let's consider some enclosure with walls made of matter. Such an enclosure must contain a gas of photons at the same temperature as the walls due to absorption and emission of photons by the atoms. Okay. Such a system, when this gas is in equilibrium, in thermal equilibrium with walls, such a system is called a black body cavity. Okay, and the photons inside are called black body radiation. A black body in the literature is normally defined as an idealized physical body that absorbs all incident electromagnetic radiation, regardless of frequency or angle of incidence. According to the classical theory of radiation, which was created in the late 1900s, if each Fourier mode of the equilibrium radiation in an otherwise empty cavity with perfectly reflective walls is considered as a degree of freedom capable of exchanging energy, then according to the equipartition theorem of classical physics, there would be an equal amount of energy in each mode. Okay, so basically wave is some kind of a wave, just radiation. Fourier mode of each Fourier mode of radiation is a wave. Okay, so with the wave we associate a quadratic degree of freedom, and so according to the equipartition theorem, there should be an equal amount of energy in each mode. Okay, but there are infinite number of modes. If we are talking about black body cavities, then all frequencies are equally probable. we can have all frequencies from 0 to infinity inside of the black body, inside of the black body cavity. So there is an infinite number of modes, and each mode has specific heat proportional to kT. That would imply immediately the infinite heat capacity. Okay, and as a non-physical spectrum of emitted radiation that grows without bound with increasing frequency. And this problem in classical physics is known as the ultraviolet catastrophe. Basically, frequencies of photons can grow without limit, and if you associate with each mode the energy kT, then the energy would be infinite. The spectral density of the mean thermal energy per unit volume and per unit frequency for a cubic black body, at least for low frequencies, it's given by the Rayleigh-Jeans law, which basically says that it's proportional to the square of the frequency and linear in temperature. Okay, and we'll talk about this formula later on. So physically, what it means, this previous formula. So there is proportional temperature, and this is the energy effectively of each mode, and this is the number of modes. You can look at this in per unit interval. So in frequency. So the number of modes per unit frequency, per unit volume is this number. And this can be visualized as the following picture. So when frequency is small, so we can fit a certain number of frequencies in the box of this kind of modes. When frequency grows, we can fit higher and higher number of modes inside of the box. And this number grows proportionally to the square of the frequency. Okay, you can imagine that once frequency is growing, we can somehow fit more modes in the box. And this is a problem. And indeed, if you compare it with the experimental results, so spectral density versus the wavelength, which is a proportional to the inverse frequency. So when frequency is low, then the wavelength is high, and indeed it displays almost quadratic behavior. Okay, but once the wavelength decreases and frequency, the corresponding frequency of modes increases, this displays this quadratic growth. And this is, as I said, the problem, because in principle it goes to infinity. But experimentally, we see instead of this curve that at smaller wavelengths or higher frequency, there is indeed a growth, but then there is a deviation, and then it goes to zero with a peak at some point. Okay, so that was one of the problems of classical radiation in physics. What we are going to do now, we are going to use the Planck Bose statistics to derive a new formula for the spectral density of black body radiation. And originally it was done by Planck, who resolved this paradox using quantization of energy. So, as we know, the average occupation number of the state with momentum p will be given by this formula for bosons, -1 instead of +1. And because photons are here, we should have the energy, but because photons are relativistic, so the energy is proportional to the momentum. So this is has a linear dependence on the momentum. The chemical potential is 0 for photons. So it's quite easy to calculate the average number of photons by simply summing over all possible occupation numbers with the given momentum. with a given momentum. And the factor 2 is because there are two possible polarizations for photons, as I explained before. So once again we do the trick, go to the integral of the momentum space or changing it to the wave space. At the end we get this as a expression for the density of photons, okay, number of photons per volume V. And this is given by this integral, or can be written this. So you see that integral goes over all frequencies, but so basically this is our spectral density. The total density is the integral over all frequencies, and this should be a spectral density or density per unit interval of frequency, per unit frequency, okay? So this is exactly the function which we tried to derive before. So we can also rewrite this density because it involves here there is a dependence on temperature. So if I change a variable, substitute beta is equal 1 over kt and denote the whole this expression as a new variable x, then I can rewrite after changing after this change of variables, I can rewrite the expression for the density in terms of all physical quantities are now in these brackets, and we see that it's proportional to the cube of the temperature density. And there is the integral given by this integral, and this integral cannot be in general calculated explicitly. It's proportional to zeta function of 3, and this is a numerical value. In a similar way, we can calculate the internal energy, total internal energy of the gas of photons. And this is a standard expression when we sum over all occupation numbers with a given momentum, and then we change to again to the integral using spherical coordinates. We change to the integral of the momentum space. Then we can change it to the integral over the frequency space, and that's what we get. And in this particular case, you see that that integral contains x squared here. Here integral contains effectively after the change of variable, it contains x cubed. And zeta functions, it's related to the zeta 4, but zeta functions at even integer values of argument, they can be calculated explicitly, and that's the answer. So after the change of variables, again here, for the total internal energy, we get the following expression, and the total internal energy is now proportional to the force power of temperature, with this constant explicitly given by this expression. So as a result, we can write that the energy, average energy of the gas of photons per unit volume is some constant sigma times temp for the force power of temperature, with this constant explicitly given by this expression. This sigma is called the Stefan-Boltzmann constant, and this is the Stefan-Boltzmann law, okay? That was derived originally by Stefan and extended later by Boltzmann. So who was Joseph Stefan? Joseph Stefan was physicist, mathematician, and poet of the Austrian Empire. He published nearly 80 scientific articles, mostly in the Bulletin of the Vienna Academy of Science. So he is best known for originating the Stefan law in 1879, that the total radiation from a black body is proportional to the force power of the temperature. Okay, so how you basically can measure this radiation? Normally what you do, you make a hole in the black body cavity and start then there will be a radiation. There will be a radiation emission from the block in all different directions, and you can look at the cool the cavity up or heat it down or heat it up, and you can calculate the dependence on temperature. So it was indeed confirmed experimentally, and so he derived basically this dependence of this law from measurements of the. Originally, he derived it experimentally from measurements of the French physicists Dulong and Petit, who calculate the law which says that the heat, specific heat of solids is just becomes a constant, okay, at high temperatures. With his law, Stefan determined the temperature of the sun's surface, and he calculated it to be 5,430 degrees and 5,600 according to the current measurements. So this was the first sensible value for the temperature of the sun. He also provided first measurements of the thermal conductivity of gases, treated evaporation, and also studied diffusion, heat conduction in fluids. And for his results in optics, the University of Vienna awarded the Leibniz Prize to him, okay? And later on, Boltzmann, he was a student of Stefan. He proved this law rigorously and extended it to apply to gray body emissions, okay? And since then, it's known Stefan-Boltzmann law. Gray body, it means that your black body just absorbs all radiations, but gray body absorbs radiation depending on frequency. Okay, so this is why it's called gray body. Okay, so if we differentiate that total energy per volume with respect to the temperature, that's what we get for the specific heat of the black body per unit volume. So, as I said before, now we can introduce the energy density per unit frequency interval. So basically the total energy is, there is a contribution from all possible frequencies. So that's the integral over frequencies. And this is quantity is naturally to call the spectral density, okay, or the spectral energy density per unit frequency. And so then this quantity becomes this. And this is the Planck distribution. For small angular frequencies, which are related to the normal frequency by 2 pi omega, it coincides with the Rayleigh-Jeans law, okay? Because for when frequency is small, this quantity here is small, so exponent is close to 1, and we can expand it into Taylor series, and 1 will just cancel, and there will be the first order contribution, and so linear in omega, and there is omega cube in the numerator, so dividing by omega we get quadratic behavior in the frequency. And that's exactly the Rayleigh-Jeans law, okay? But for large omega, it decreases exponentially, as you can see here. And Vienne, in around 1896, he suggested that this law, exponential decrease of the spectral density at large omega. So there should be, when frequency is large, this number is large, you can neglect this -1 and you get exponential decrease in frequency. So this was Vienne's law, and Planck's formula basically glued together this Rayleigh-Jeans law and Vienne's law. Basically, it connected these two laws. So Max Planck, He was a German theoretical physicist who discovered a quantization of energy, which won him the Nobel Prize in 1980. He was also very gifted in music and played piano, organ, and cello, and composed songs and operas. However, instead of music, he chose to study physics. There is quite an interesting story because originally his supervisor, Munich professor Philip von Joly, advised Planck against going into physics, saying that in physics almost everything is already discovered, and all that remains is to fill a few holes, and that what was around 1875. Okay, Planck replied that he didn't want to discover any new things, but only to understand the known fundamentals of the already basically finished field of physics. And so he began his studies in 1874 at Munich. In 1900, Planck proposed his famous black body radiation law based on his postulate of quantized electromagnetic energy. At first, Planck even didn't believe himself in this quantization of energy and used it as a useful mathematical trick to derive this law, which perfectly describes spectral density at low and high frequencies. In 1911, at the Solvay conference, he talked to Einstein, and Einstein was able to convince Planck. And soon after, two scientists became close friends, and in 1920s, Planck expected that the wave mechanics would soon render quantum theory, his own child, unnecessary. There is quite an interesting quote from the Planck, and he actually experiments the truth of his own early observation from his struggle with the older views in his younger years. He says that a new scientific truth normally does not triumph by convincing your opponents and making them to see the light and accept your point of view, but rather because all your opponents eventually die and a new generation of scientists, physicists, they grow up which are familiar with these concepts and accept it without question, okay, without much arguing. So in 1948, the German scientific institution, the Kaiser Wilhelm Society, was renamed to the Max Planck Society, which is now, probably you all know, it's a very large society, and it includes 83 institutions in all basic German cities, representing a wide range of scientific directions. Okay, so once we know the total energy, and density distribution, we could calculate radiation pressure exerted on the wall from photons kinematics. We've done it already before for the classical gas. It's all the same. We take a small unit with small cylinder with a unit area, and we calculate how many molecules reach it at a unit time, and depending on the angle, if the horizontal is the horizontal component of the velocity, this is a particle's momentum direction. So there is a momentum transfer towards the wall, and then we can calculate the pressure by integrating the flux multiplied by the momentum transfer. We've done it at least twice before. Okay, so once we integrate over the angles in the interval from 0 2 pi over 2 and substitute the formula for the Planck density of states, what we get, we obtain the equation for the pressure. And comparing to the equation to the total energy, we can see that the lower the relation between the pressure, volume, and the energy changes, okay? So originally, we showed that for all classical and for fermions and for bosons, the law looked like PV equal 2/3 of U. But in this case, our particles are moving very close to actually photons moving at the speed of light, massless particles. But this relation holds even for massive particles at temperature so high that they move at they move close to light speed. Okay, so basically, what happens when for slow-moving particles we had 2 here, and the reason for that was that the energy dispersion relation was quadratic in momentum. For relativistic particles, it's linear in momentum, in the particles momentum. So 2/3 for relativistic particles is replaced by 1/3. And final comment, our universe is filled with black body radiation at temperature approximately 2.7 degrees of Kelvin. And this is a cosmic background radiation thought to be a relic of the Big Bang. And this is the experimental plot of this cosmic radiation depending on the temperature, and you see that it fits the Planck law very well. Okay, the next topic will be what's called Bose enhancement, and I will continue it in the second part.